So we have already seen that the value or the expression for the average probability of error, but I want to give a more precise formula that expresses probability of error in terms of signal-to-noise ratio. So from this expression, we have seen that probability of error is given by a half complementary error function x1 minus x2 all over 2 root 2 sigma. Sigma is the standard deviation of the noise or the AWGN noise. So we can now express this equation as follows. You see the probability of error that the received variable x is in error. We have seen that it is given by 1 over 2 ERFC x1 of t minus x2 of t divided by 2 root 2 sigma. And now we can say let p of t be equals to x1 of t minus x2 of t. So replacing this in our equation, we are able to find the probability of error of our received signal x is going to be given by ERFC or complementary error function, which is also the one we refer to as Q function, to be pt all over 2 root 2 sigma. We can decide to square this function. We square everything here, and then we root that entire function or variable in the bracket. What that will give us is that is half of q of p squared t all over 8 sigma squared power half, and we know that the signal to noise ratio is normally given by the energy of the signal that is being transmitted divided by the energy of the noise that is accompanying the signal, and therefore I'm just adding this square to represent what we have here. So if I decide to remove that square, we can say that the maximum signal to noise ratio gamma can be expressed as such, and therefore we need to replace it in this equation so that we are expressing the probability of error in terms of signal to noise ratio. We are going to see that probability of error of x is going to be given by half q of gamma max squared divided by 8 power 1 over 2. So that becomes our standard or generalized equation that we use to represent the probability of error, given that we know the signal to noise ratio. Now, from this expression of probability of error, there's something here that we know about the AWGN noise, that sigma squared, the one that we have found at this point is the variance of the noise, which is equivalent to power spectral density of the noise. And we can also be able to express the power spectral density of the noise as N0 over 2. And in similar manner, the gamma max squared that we have expressed as the value of p squared t, this is definitely can be expressed as the power spectral density of the difference between the two signals that we are transmitting. However, for us to be able to find the actual power that is contained in the difference between these two signals, we need to be able to express this one as the integral. So we actually say that the gamma max is also can be represented as this, which is integral of over the one period of p squared dt divided by this sigma squared. But since this is a constant, we can put it outside, and therefore becomes 2 over n0. So for that reason, that becomes our expression of gamma max that we are going to be using to find the probability of error for different modulation schemes, and therefore we can express it as a probability of error is equal to a half ERFC of gamma max squared divided by 8 power 1 over 2, and where gamma max is going to be expressed by this expression right here. So now we start with finding the probability of error of ASK. That is the very first one that we looked at when we were looking at the modulation schemes, and this will be the first modulation scheme that we are going to evaluate its probability of error. And for that reason, we know that we represent the signal of ASK in this form, where we have zero voltage, we have zero, and when we have a voltage, a carrier that is having maximum amplitude of A to be used to represent a symbol 1 or binary 1. So this is 0, 1, 0, etc. So what we know is that symbol 1, or which is also represented in the binary 1, is represented by the amplitude which we are referring to as x01, which is A cos omega c of t, and similarly the binary 0 is going to be represented by x02, which is equals to 0 voltage. And from what we have been able to define P of t, we have said that P of t is equals to x01 minus x02, and when we follow these two values, we say that this difference is going to be given by A cos omega c of t. Now, to find the value of gamma max so that we can be able to find the probability of error, we know that gamma max squared is equivalent to 2 over n naught, 0 to t, 1 over 1 period of A cos omega c of t dt, and we know that of course this one is squared, and we know that because we are talking about p squared, therefore this would be squared and this would be squared. So that is the value we are using here. So having said that, we say now that we know that cos of omega c of t squared is equivalent to a half 1 plus cos 2 omega c of t. Therefore, when we replace this here, we are able to find gamma max squared to be equivalent to this can come here to cancel it out, so that we have 1 over n naught. You can put a squared there, and therefore we have integral of 1 dt plus from to t plus the integral of cos of 2 omega c of t dt. When we perform this integration, we are going to find that gamma max squared is equals to a squared over n naught. This becomes t, whereas this one becomes plus sine of omega c of t, 2 divided by 2 omega c. This varies from 0 to t, but there's something we know that this top or numerator varies from -1 to 1, whereas this is a high carrier frequency. When you divide 1 divided by high carrier frequency, this term turns to 0, and therefore we are left with only these two terms. Therefore, we are saying that gamma max squared is equivalent to e squared t all over n naught. And now, because we're looking for PE of ASK, we can now say that this is equivalent to 1 over 2 ERFC, and our bracket says that this is going to be e squared t all over 8 n naught. Remember that we had an 8 where we were dividing this 8 here. So of course we say this is to power root. So when we continue down here, we say that now we know that from our knowledge of signals that the energy of the signal can be expressed as a squared over 2, where we can see that this is the signal or the symbol energy or energy per bit or per symbol, and therefore we replace a squared over 2 with e, and we consider the period to be equivalent to 1, then we can say that probability of error for ASK can simply be found to be 1 over 2 ERFC of E divided by, of course, this term becomes, let me just break it down here, E squared over 2, we have said t is equals to 1, so 1 divided by 4 n naught. This is the term we are breaking from that, and therefore when we have replaced this one with e, we are left with 4 n naught, and this is to power half. So officially this is the value of probability of error for an ASK signal, as we have already found out. So that is how we analyze the ASK modulation scheme in terms of its probability of error.